This is the second tutorial for calorimetry, and here I've written down the formula that I told you in the last tutorial, and I'm going to start off. I told you in the last tutorial I'll be telling you what the C is, specific heat capacity, what it exactly means. So specific heat capacity, the symbol for it, heat capacity, the symbol for it is a small c. It's just a small c. Now it's defined as if you take a substance of unit mass, it's the amount of heat energy you need to raise the temperature by 1 degree Celsius or 1 Kelvin. So we're saying take a substance, take unit mass of the substance, and we're saying 1 degree Celsius or 1 Kelvin. The reason why we say or 1 Kelvin, you must be wondering, doesn't it mean two different things? But if you look at the scales, if you look at, so you have two scales over here. The first one is degree Celsius, second one is Kelvin. Let's just make 2 marks here. This is 0 degrees Celsius, we're talking about degrees Celsius here, and say this is 10 over here. Now, I'm sure you learned how to convert degree Celsius to Kelvin in grade 7 or 8, or maybe 9, I don't remember, but you just add 273. It's actually a little more than 273, I think, but for now we take 273. So this is 273 here, and for the 10 it'll be 283. Now in this formula, if you look here throughout this chapter, we're referring to delta T, not T. And I told you delta T means difference in temperature. So when we're talking about temperature here, we're looking at the difference between the two values. Look at the difference in the degree Celsius scale, it'll be 10. Look at the difference in the Kelvin scale, it again is 10. So what we can say is that the value of 1 degree Celsius and 1 Kelvin is the same. If you increase the temperature of a body by 1 degree Celsius, it will be the same as increasing the temperature as 1 Kelvin. The values are the same. But this is not the case with Fahrenheit. So we only say degree Celsius, or you could say Kelvin. But in most cases, to be safe, you should say Kelvin, because Kelvin is the SI unit. And also, one more thing, I'm sure you know, but just to remind you, you never write 1 degree Kelvin, that's wrong. You always write just 1 Kelvin, and it's 1 degree Celsius. So, coming back to specific heat capacity, these are the 3 things given in the definition. Now, the formula for this is that C is equal to Q, which is heat, upon M into delta T. Okay, Q upon M into delta T. If you cross multiply, you'll get this relation over here. You'll see that. So you can see there's an M in the denominator here. When I tell you about heat capacity, I'll come back to this. So now heat capacity is denoted by C dash, and it's a capital C. Heat capacity. Just note that we've removed this specific from the term, so it's just heat capacity we're talking about. These are two completely different things here. So heat capacity of body is the amount of heat energy you need to raise the temperature of a body by 1 degree Celsius or 1 K. So you have any body, whether it's shaped like this, or it's just a small particle, or it's a bottle or something. So that looks more like a key than a bottle. But the point is, if you have different objects, they'll all have different heat capacities. That depends on their mass. Okay, so over here we're talking not about a substance, but in the definition we say body or an object. We again said 1 degree Celsius or 1 K. And that's all. Now compare these two. The only thing missing here is unit mass. And over here in heat capacity, we're talking about a body, not a substance. So if we say what's heat capacity of copper, that's a wrong statement. copper doesn't have a heat capacity, it'll have a specific heat capacity because copper is a substance. Same way, if you say what is the specific heat capacity of a frying pan, again, it's a body, it's a substance. You can't have a specific heat capacity for it. So now, heat capacity, even though you're not mentioning mass over here, it depends on mass. Okay, it depends on mass. Over here we're taking unit mass, so mass really doesn't bother us because whatever substance we take, taking unit mass of it. So don't get confused over here. We're mentioning mass, unit mass here, but that doesn't mean that specific heat capacity depends on mass. It does not depend on mass at all. Also, I have to tell you the formula for heat capacity, and that is simply Q upon delta T. Now, I'm just going to ask you to figure out the SI units for this. For that, all you need to do is put in the SI units of these variables over here. So Q is energy, heat, of course. So it's joule. Then the denominator, you look at mass, which is kg, and then you look at temperature. SI unit is Kelvin, not degrees Celsius. So SI unit is actually joule per kg Kelvin. And now you look at C dash, that's heat capacity, and you'll see it is just joule by Kelvin. And this, again, I'm saying that despite there not being a kg over here, this actually depends on the mass because your Q is in turn going to depend on the mass. Over here, this kg represents unit mass. You'll understand it when I explain it a bit more in a few minutes, but I'll leave it over here if you don't get it. Also, just to sum up a few differences now. Say you have CE over here and C dash here. Specific heat capacity is for a substance. Heat capacity is for a body. So specific capacity is, for example, copper. Heat capacity is example for a wire, a copper wire. So that's the difference. Specific heat capacity does not depend on mass. That looks like Mars. I'm going to write it again. Okay, that's no better, but I think you know what I mean. And this depends on mass. And then the last difference is, of course, the difference between the formulae and the SI units, which you can see from here. So now I'm going to rub this out and come on to the next section of this chapter, which deals with the principle of calorimetry, which is a very important part of your chapter here, main part actually. So there's a chapter where you're going to get a lot of numericals. There's very little theory. It's all for the theory actually. So now a calorimeter, I'm going to tell you very briefly about it. There are a few reasoning questions which you should know about over here. That's given in your book. But calorimeter, sorry, not metry. A calorimeter is it's a sort of vessel. So its main use is to measure amount of heat gained or even heat lost by a body. You just place inside. There's a whole fancy method to do it, and that is given in your books, and it's very long. There's nothing tricky about it really. You just need to read it thoroughly and you'll get it. So I'm not going to go over that, but principle of calorimetry, or it's also called the principle of mixtures, very important. I'm going to write the mathematical form and also just the English form of it. What it says is that heat lost by body is equal to the heat gained by the cold body. I think you guys have already known this, but now we're putting it in the form of a principle. It's a fact, and it also shows conservation of energy, because remember that these are both energies over here. It's heat energy. So it shows conservation of energy because the whole energy is getting transferred from hot body to cold body. And this, I will refer back to the example I gave before, that using uh, your knowledge of the temperature of two bodies, you can tell which one is the hotter body, which one is the cooler body, and so where will the heat transfer take place. So the one that has more energy will give its energy to the one that has lesser energy. That's it, and they're mathematically equal. So if you can just put into place the formula I gave you in the first section, that is Q is equal to mc delta T. So you can say that if you say you have two substances or two bodies, so the mc delta T of the first one equal to the mc delta T of the second. Now remember that this whole process of transfer of heat energy will take place until the temperatures are the same. It'll only stop when the temperatures become the same of both the bodies. So say the hotter body has a temperature T1, say the cooler body has a temperature T2. Now you can and say that the temperature that they come to an equilibrium at is T. You can take T3 also if you don't want to get confused with the whole number thing not being in order and all that, but I'm taking T over here. So just imagine this is the hotter body on top, so T1 will definitely be more. It's going to lose energy, so T1 is greater than T2, because T2 is a cooler body, the temperature will be much lower. So T1 is going to transfer some of its energy. How much depends on a lot of things, until T1 is equal to T2 is equal to T, and by T1 equal to T2. T1 here I'm referring to the temperature of the first body, T2 is second body, and T is the final temperature. So if you look at it, the difference, the delta T for the hotter body is going to be, we can write it as M1 C1 T1 minus, because T1 is definitely greater than T, and this is equal to M2 C2, and we write the opposite now, T minus C2. And why is it? Because this is the sort of relation between them. T1 is greater than T is greater than, not equal to, greater than T2. So now to get a positive, when you subtract, you're going to subtract T2 from T. So T minus T2 comes over here. So this is your formula, and you'll be using this for all your numericals. You should know this. Also, one more thing, I think I forgot to mention it before. When you have, sometimes you have an electrical source rather than just heat. You supply heat in the form of electrical energy, so that's called the electrical method. And remember, that's also energy. And if you refer to your electricity chapters, you would have come across energy is equal to P into T, and this energy is converted to heat energy, and that's equal to Q. This is equal to mc delta T. So if at all they've given the power and the time to you instead of heat energy, you need to find this, or vice versa. Pick this and they tell you to find power and time, just use this, that Pt is equal to mc delta T. It's the same thing. And remember that in this whole principle of mixtures, principle of calorimetry, we're assuming that the efficiency is 100%. It'll never be 100%, but over here we're just assuming it to be. And the same thing in the electrical method. Not all of the electrical energy will get converted to the heat energy, but just for convenience over here we're assuming that. So I'm out of time over here. In this section they're also given a whole huge method, huge formula as well on measurement of specific heat capacity, of any solid or liquid. Now, that's a huge formula to learn up, and honestly, you don't really need to. If you've got this concept, you can write down the formula and all the information on the spot as well. So I suggest you don't learn it. Go through it definitely, but don't learn it. And also, they've given you, uh, I don't know if I mentioned it before, but the specific heat capacity of water is very high, and I mean very high in comparison, of course, to other substances. And this has many consequences which are listed down very nicely in your book. So you could look at all those because they're very important, and they can come as what, 1 mark, 2 mark questions. And also, there are a few more reasoning questions on how high and low thermal capacity, or that's not specific heat capacity but just heat capacity, how those are applied. So I'm not going to cover those, you can do those yourself, but if you have any doubt you can ask us. But that's for this video. I'm going to continue this with latent heat and a few numericals in the next.